I should
sorry.
continue. Yeah, so for today I had in mind to talk with you on high-end sea level rise, which is a kind of effort we are taking within the framework of the WCRP Grand Challenge team. And that means that there are a lot of people involved. The Grand Challenge is one of the WCRP programs, and you see here, I hope you can see my pointer here. That's us, that's regional sea level change and coastal impacts, but of course it's also very much related to what is ongoing on the ice sheets, as I will come to, because the Antarctic ice sheet is playing a major role in the discussion on high-end sea level rise. So it's a lot of people involved, and rather than listing all the names of the people involved, I've made a picture, or a composite picture, of all the people who are involved. It's around 30 people who contributed to this work. And you see a nice picture, and I suppose you might recognize some of them, but probably not all of them. And somehow they contributed in providing information on the different components which play a role for the high end, or on the approach which we have been taking to get to a high-end estimate. So what do we mean with a high-end estimate of sea level rise? First of all, we're talking about the high end of the trend, which is not to be confused with extreme sea level, as I will show in the next diagram. And this is basically evolving from the discussions which are circling around in the IPCC context, where sea level rise is often presented with a likely range, as indicated here with this part of the PDF, where it often stops with a likely range estimate. And at the same time, there is a stakeholder need for knowledge on what is happening in the tails of the distribution, and that is what we loosely define here as the high end. Some people call it the worst case, but to me, a worst case is always like you melt Antarctica in a day. So that's not a very practical value. So you should come to a value which is high end, which is still plausible and reasonable to work with for stakeholders. That's a little bit the thoughts which are behind the high-end estimate, in my view. So it's not about the extreme temporary events which are leading to floods, but of course those extreme events are superposed on the increase in the mean trend. So the flooding events will definitely increase in frequency and magnitude by the fact that the mean trend is increasing, but the high-end estimate is really referring to the trend. So an attempt for a definition, because this is a kind of a tricky term, I think, is a high-end sea level projection uses multiple lines of evidence and physical implausibility to constrain the estimate of sea level rise independent of a stochastic description. I've made up this definition recently, so it's still a little bit floating, I would say, but it acknowledges the fact that sea level projections are only partly stochastic and partly deterministic, but you never capture everything in the projection itself, and you need to know your limitations. And but the fact that you never capture all the physical processes, it means that you cannot completely treat it as a stochastic variable. So starting with a little bit more background, I like to start off from, and I think that's still justified to do, with the SROC projections in which I was involved, which were published in 2019. And they have the sea level projections, and well, in fact, it doesn't matter. You can also go to AR5 or all the reports from the IPCC. And what you will see is that there's always a band which is the likely range, but it doesn't define on what's happening outside the likely range. And in this case, the SROC projections show you for the RCP 8.5 scenario, a much higher value than the AR 5 report already in the median value, but still people or particularly stakeholders which are risk adverse were not very pleased with this result as such, because it doesn't answer the question what is the high end, particularly not in 2100. Most stakeholders are a little bit biased to shorter timescales than 2300, but there's getting more and more interest on what is happening after the turn of the century. And also they would like to know what is the kind of maximum or the high end which is possible. And this is usually not addressed in IPCC reports. And of course, that is related to the fact that projections get very uncertain on longer timescales. So I think the SROC report was the first to have a kind of really projection up to 2300 with a likely range, although there is some work already presented in the AR5. It went a little further, and clearly it makes a difference between medium and low confidence depending on the time scale, but that's still not sufficient. And the first attempt to address this in a little bit more satisfying way for risk adverse stakeholders was made somewhere in the summary for policymakers of the SROC report, where it said that while stakeholders with a lower risk tolerance, so particularly those deciding on critical infrastructure, should also consider values outside the likely range and from methods characterized by lower confidence, such as from expert elicitation. So in fact, what the SROC report does here is that they defer those who are interested in a high-end estimate, not to the SROC report, but go and have a look in expert elicitation approaches as an alternative to find values which are maybe more appropriate for your risk adverse decision process. So this is clearly, this topic is clearly at the interface between scientists and decision making. Usually we as a scientist, and supposing that most of the people in the audience are belonging to the left part of the figure, the scientist, rather than the decision making, but this is an assumption I make, which I'm not sure whether that's justified, but it doesn't really matter. I mean, the way scientists typically think is that they discuss high end in terms of uncertainty, scenarios and likelihood, and a decision maker is having different questions to the same problem. He needs to, or she needs to know how much and when to adapt, and that's a different question. So you may have to take that into account in framing your high-end numbers. So what are the options for getting to a high-end value? First of all, from a physical point of view, you would say the most logical choice is to take an Earth system model and then provide a PDF in the end. But unfortunately, many of you will know that that's not an option at the moment, because in fact, Earth system models do not have a fully coupled ice component in terms of sea level rise. So we tend to first run an Earth system model and then offline calculate the sea level contribution based on the output of the Earth system model. And thereby you ignore all kind of feedbacks. And this has several reasons why we do it like that. First of all, the glaciers are on a very small scale, so they're very difficult to capture by the coarse grid size of Earth system models. That's one argument for the glaciers. For Greenland, we are getting to very close to, I would say, coupled models. The first successfully coupled models are around now, which is mainly due to the fact that the surface mass balance of the Greenland ice sheet can now be calculated reasonably well for in an Earth system model, or at least in a few Earth system models are pretty successful in that. But Antarctica, that's a desire which is around already in the community for 10, 20 years, but the progress is still limited, and I think that has different reasons. One is that calculating the surface mass balance of Antarctica is very complicated, but above all, it's currently recognized, I would say, that calculating the basal melt below the ice shelves is even more complicated, and there are no good solutions in Earth system models to do that. All these solutions which are around are highly parameterized. So, and for that reason, it's in fact all an offline calculation based on an Earth system model result. So it's clear that this first option is not providing us all the answers which we would like to have. So the typical style in IPCC and many of the sea level projections is that you use, and that's the second point here, that you use a deterministic ice sheet model, and well, you try to use that as input for ice sheet models or ice melt models, which are then added up to what you get from your ocean component, for instance. A third approach, which is around to get a high-end estimate, is a probabilistic approach, and then you have to think of the papers like the one by Bob Kopp in 270 or Davy Labar, and they get a full PDF for the sea level projection, but that's usually based on the assumption of an Antarctic contribution, for instance, from a single study. In both these papers, it was taken from the Continent Polar 216. So it doesn't really, it provides you a PDF, but it's not how to say that, a realistic PDF, because the variability in Antarctica is in fact not taken into account. So, and it doesn't quantify processes which are not in those models, obviously. And as a fourth possibility, there is the structured expert judgment, and that refers mainly to the papers from Jonathan Bamber from 2013 and 2019, and those provide a high-end estimate, but it's a little bit questioned whether the outcome results on the choice of the experts and what the experts have in mind. You don't know that with that approach, so it's not transparent, and stakeholders want to have a transparent approach which they can judge themselves. So that's also not a completely satisfying approach. And finally, there is the what I would call the plausibility approach, which dates back actually as a classical paper, at least to Pfeffer et al., who provided kinematic constraints to ice flow rather than an upper bound to get a high-end estimate. And that was an interesting approach at that time, but it also assumes kind of ad hoc assumptions on the acceleration of ice flow. So that's also has its limitations, let's put it that way. So a couple of years ago, we had a couple of discussions on how can we improve that, and that resulted in a paper which I call the Stamm et al. Framework paper, which describes a qualitative description of the high-end estimate of sea level rise for stakeholder applications. So really having this focus on the stakeholders. And you probably don't, or at least not everybody will know this paper. So this paper proposes, in fact, that the stakeholders can use the PDFs from an IPCC report, depicted here on the left side, and that provides them with an upper end of the RCP scenarios. But then the question is, how far do you want to stretch that? What do you want to add to what is provided by the IPCC? And in that paper, we propose that you're explicit about this, and that you can include building blocks, as we call it at that time, which you include to add to your high-end sea level projection. And these building blocks, they vary possibly over time. So what you see here is different time scales, 10 to 50, 100 years, and more than 100 years. And depending on your risk adverseness, you include a building block in your high-end estimate or you don't do it. And here I have a couple of examples of building blocks. And for instance, if we take the collapse of the West Antarctic ice sheet, the idea was that's a building block. If you look at a time scale of 10 to 50 years, it's on the right side of this gray bar, and probably nobody or no stakeholder will include it in his high-end estimate. But by the time that the time scale is 100 years or a bit longer, you may decide that you take that into account in your estimate of the tail of your sea level projections. And of course, the longer you wait, the more you can, more building blocks it's reasonable to take into account. But at least you're then explicit on what you do in order to get your high-end estimate. So against this background, this was this was published in 2019. We thought it would be, this is all conceptual, and in the end, I mean, you want to come to numbers rather than just this concept. So we try to improve on this, and we thought it's time to try to really quantify this high-end estimate, and we do that a little bit with an approach which we take from a paper from Ted Shepard, which is a storyline approach. And the idea behind this is that you identify physical, self-consistent, plausible pathways, and you move a little bit away from what will happen to what is the impact of. And by that mean, you don't want to create false alarms, but also you don't want to have missed warnings. So it's a kind of a balancing act between what is useful and realistic, and what is completely nonsense, like melting Antarctica in a day, and also ignoring that there are processes which are not taken into account in models is also kind of stupid approach. So somewhere in the middle, you have to end with values which make sense. That's maybe another way to frame the outcome of such an exercise. So for climate risks, for instance, in this Shepard paper, they take the approach that you have climate sensitivity and forcing that leads to global warming, and etc., and it leads to hazards, and then based on vulnerability and exposure, the classical items in IPCC context lead to a climate impact. So this idea of a causal chain of processes is what we try to apply to the sea level context. And I'll show you how we do that for Antarctica, where the Antarctic ice sheet is one of the contributors to sea level rise. So you have the sensitivity and the forcing. It leads to a temperature change. This temperature change on Earth leads to changes in the environmental conditions in Antarctica, which leads to changes in surface melt and in bottom melt. And these surface melt and bottom melt will eventually influence the ice shelf breakup together with processes like hydrofracturing and calving. And this ice shelf breakup is considered to be critical because once the ice shelf breakup takes place, there are a couple of instability mechanisms, the marine ice sheet instability and the marine ice cliff instability, which can lead to a very high sea level rise. And obviously, the other alternative is that the sliding conditions at the bed change a lot, also contributing to a very high sea level rise. So once the ice shelves are gone, as the idea, then these three physical flow mechanisms, they can add to a pretty unconstrained sea level rise, I would say. And obviously, the time progresses from left to right here, and the time scale is obviously not very well constrained because we don't know when this all will happen, or at least we don't know this with a lot of detail. So if we go to the different components of sea level rise, and we make the considerations which are relevant for the high end, in particular sea level rise, and we look first to glaciers, we argue that the glacier contribution to sea level rise is very much temperature controlled. And we have a pretty good insight in temperature projections relative to all the uncertainties in the Antarctic processes. And the glacier MIP experiment from the paper from Marseillon et al., there they have 10 different GCMs, 10 different models, and that provides you with a reasonable estimate of the high-end glacier contribution to sea level rise. There are a couple of tricky issues where you have to take into account that there is a part of the glaciers which is below flotation, and in the end, most of the glaciers are melted, so you have to correct for that also, because we typically in this exercise, I think I did not mention that, but we consider two scenarios as contrasting scenarios, 2.6 and 8.5, and two timescales, 2100 and 2300. And for the glaciers, this mentions then per timescale and per scenario the different processes which we believe are important in this small table. For Greenland, the idea is that for the 21st century, the contribution to sea level rise is fairly constrained as long as the temperature change is small. So an ICP 2.6 scenario, we probably can use the ISMIP results, which have been coming out over the last 1.5 years to get a reasonable high-end estimate. But one of the problematical issues with the Greenland ice sheet, or the possible mass change of the Greenland ice sheet, is the fact that we have seen a couple of years since 2010 where the melt was extraordinarily large, which was most likely related to circulation changes in the atmosphere. And we also know at the same time that the CMIP type of models are not reproducing these circulation changes. So there we have a clear problem that we cannot rely on CMIP models to provide us a good high-end estimate of sea level rise from the Greenland ice sheet. That's one argument. And the other argument which complicates an estimate from Greenland is that it's also recognized that not all the feedbacks are in the model. And there's the general idea that there are more positive feedbacks which are not incorporated than negative feedbacks. And for instance, the blackening of the surface is one thing which is usually not taken into account, or the albedo decrease related to more meltwater on the ice sheet is also often not taken into account. And that all leads to, the bottom line is this all leads to lower albedos and therefore more melt. And then another complication for Greenland is that there is a tipping point, possibly between 2 and 4 Kelvin, depending a little bit on which study you tend to believe. But that has also repercussions, of course, for a high-end estimate. So for Greenland, it already gets a little bit more complicated. Outlet glaciers are probably only important for the high end, for the low scenarios up to 2100, and after that, for at least the high end, most outlet glaciers are retreated and they're not particularly relevant anymore for the high-end estimate. But you get these processes on the albedo feedbacks in the atmospheric circulation, which make it more difficult to come up with a useful estimate for a high-end estimate for the Greenland ice sheet. And for Antarctica, as I already mentioned, there is a whole zoo of processes which are poorly known, I would say, but and also for which the time scale and the temperature change where they're relevant is not always very well defined. In first instance, we had the idea that estimating the Antarctic contribution to the high end for a low scenario in 2100 could not be so difficult. There would probably not much changes in Antarctica, but well, further studying of the literature revised that a little bit, particularly because of the alarmip outcome, but also a couple of papers arguing that you could get a switch in the cavity circulation from cold cavities to warm cavities, in the end leading to considerable contribution from Antarctica also for a low-end emission scenario. And well, the other processes are already mentioned in this first figure on Antarctica. They all contribute somehow to an estimate of the high end for the Antarctic ice sheet. So trying to summarize this in numbers, in the end resulted in this table, and there are many, well, maybe not many, but there are quite a few studies behind these numbers, depending a little bit on which number you look at. Of course, the estimates for the further in time are restricted to a limited set of publications, and the papers are often treating the scenarios up to 2100, so the amount of literature available is much larger on the earlier part, obviously. And if you add that up, you can come to values like roughly a meter for 2100, 1.7 for 2100. So this looks to be a little smaller than what you get from an expert elicitation exercise. And this is probably a number which is a bit higher than most people would think, I believe. And it also shows you that the high-end estimate for the long term is a pretty terrifying number of 10 meters, order 10 meters, which is essentially, of course, related to the enormous contribution from the Antarctic ice sheet. And this is, Greenland is much smaller, but that's a very, I should say, very weak number. It's a very limited number of studies available to make this estimate. But anyhow, the number is, of course, enormous. Of course, this is all a little provisional. We're still digesting this, but I think we hope to get to a kind of manuscript in summer somewhere. So then we should have finalized the numbers eventually. There are a couple of issues to discuss, I think. One is that what we did in the previous table is simply adding up the different terms. But yeah, that's a little bit the question whether that's allowed to do. There are a few papers around arguing on the correlation between the different components, particularly a paper which I was involved from one of my postdocs, analyzing GCM results and quantifying the correlation between the different terms in the different GCMs. And at least in the way the GCMs are used to calculate those different contributions in the literature. So what you can clearly see is that they're definitely not uncorrelated. So the question is a little bit whether you can simply add up the high-end values from Greenland and Antarctica and glaciers and thermal expansion in order to get the best estimate of the high end, or whether you then underestimate the high end because they are partially correlated to each other. So that's a little under discussion, but given the fact that this high-end estimates is based on process uncertainty rather than climate uncertainty, it seems to be justified to treat them, at least for the global values, kind of independently, is our current thinking. Another issue which you may have seen passing by in your mailbox recently, which I like to address briefly, is this paper from Conto et al. In Nature 1 month ago, I think by now, addressing also in a way the high-end contribution from the Antarctic ice sheet to sea level based on combination of collapsing ice shelves and enhanced ice flow by marine ice cliff instability. And that result is in fact quite in line with what we have here for the high-end estimate, in the sense that it goes to very high values in 2300, and that it's still at the more or less same numbers as we have in the high-end estimate for 2100. So the difference with this older work is essentially that the ice shelf collapse takes place after 2100, and then the contribution to sea level can only take off once these ice shelves have collapsed. So that's very much in line with most other modeling studies now. So I think this is a nice result which fits very nicely in this discussion on high end. And what they also bring forward in this paper, which is a discussion which is not very often made, I would say, is the fact that meltwater from the Antarctic ice sheet could have a major impact on the ocean circulation around Antarctica, and that's at least the difference between the blue and the red in my understanding of these simulations, and that's a kind of additional uncertainty, I guess, which we should try to think of in more models to try to quantify this effect, this feedback. So in conclusion, I think from an adaptation perspective, there are very large differences in the adaptation efforts between 2 and 4 degrees in 2100. That's this difference between 1.1 and 1.7 or so. Beyond 2100, I think we show clearly that there are very different futures in terms of sea level rise, and the sea level rise is so large under the high RCP scenarios that a lock-in situation in terms of adaptation is looming on the longer timescales. So in a way, this is also a plea, I would say, for emission reductions, because the sea level will not be adaptable to on the long term if the temperature is really going to increase according to an RCP 8.5 scenario or so. And that at the positive side, this contrasts very much what seems to be reasonable for RCP 2.6, in the sense that even on the long time scale after 2100, adaptation remains feasible at many places for an RCP 2.6 scenario, also on the long time scales. And finally, a point of discussion which was around for a long time in the community, in the sense that the outcome of the expert elicitation pointing to the 2-meter GMSL in 2100, is that really unrealistic if you follow this storyline approach? Well, 2 meters, I would say, is unrealistic in the sense that we don't get there. if we add up the different components as we did in this study. But at the same time, it's not that far off from it anymore. So definitely locally, the variations are probably on the order of 20% with respect to the mean. So locally, the 2 meters can definitely not be excluded anymore, I think, in terms of a high end. I mean, definitely not as a mean projection, but as a high end. The idea is that we cannot exclude it any longer. So that's more or less where I want to leave it. And the final slide where I would like to point a little bit to is the critical issues which we believe are needed to improve upon in order to constrain this high end better for glaciers, Greenland and Antarctica, which is of course for Antarctica a whole list of physical processes which need to be improved upon. So that's where I want to leave it, and that should allow some time for discussion, I hope.
Thanks very much, Roderik. That was a really interesting talk. Do we have any questions or points from the group? Feel free to write in the chat or to raise your hand or just speak out. Oh, there's a question from Klaus.
Yeah, as a former member of the NPCC, the New York City Panel on Climate Change, and not being an expert in that field of science, I'm more a user of it. So I feel almost embarrassed that our 90th percentile value for New York City is in the order of the 2 meter range, and the what we call the Antarctic rapid ice melt scenario is approaching 3 meters. So clearly, when people will refer to your paper and your thinking approach, they'll say, oh, they call 1 meter a higher end and you come out with 2 and 3. What are, in your view, even so you commented on that in your last few sentences, the reasons that we came out with such a high value? I know it was a probabilistic approach, and Bob Kopp and others fed into those forecasts, but can you comment further on this?
Well, the original ideas which led to these high values were leaning very much on a high-end contribution from the Antarctic ice sheet, which was essentially based on the Continental Polar 216 paper, which caused, I would say, a lot of discussion in the community, essentially burning down, I would say, to the fact that the melt rates in the Continental Polar paper from 2016 were too high, at least too high in comparison with regional climate models, and in that sense, people started arguing that the sea level projections, which included the Continental Polar 216, were too high. But at the same time, I think we have seen over the last 5 years a process where other components like the Greenland ice sheet could also possibly contribute more than previously thought, like the circulation issue, which was not recognized, I would say, in 2016, still not. Those papers addressing that effect, which is in fact an increase of a factor 2 for the Greenland contribution are from the last few years. So they partly compensate the fact that that some studies tend to dismiss the continental pollard. So there is a kind of balancing between the different components, which in the end comes back to this 2 meter as a kind of reasonable estimate for the high end if the emissions are not very strongly reduced. So it's a change of insight, but which is physical insight underlying all these estimates, I think, but not in the number in the end.
Well,
does it answer your question?
yes and no. I mean, I wish I had someone here who had more insight. What was the process for the NPCC to have the outcome of 2 meters for the 90 percentile? Unfortunately, I cannot do that. I'm not sure whether it really relies simply on the Pollard paper that much. So I'm still concerned that you have 1 meter and we have 2 meters, 2 to 3 meters for 2100. Anyhow, enough.
May I interject, Klaus? I think some of the other considerations were the ongoing glacial isostatic adjustment, the fingerprinting, you know, with the possible impact of Antarctic ice melt, creating higher than average sea level rise for New York. And then also thermal expansion was locally higher than globally average. And all of those adding together, in addition to, you know, making the assumptions about the high end contributions from Antarctica, added up to that high number.
Yeah, that's correct. What we are referring to here is really the global mean values, and it's in every estimate, the regional values show up the highest number in New York because of the arguments given by Vivien, GIA, Antarctic contribution, and the ocean components. They tend to be all slightly above the mean value for the New York area, or the more general, the east coast of the US, implying that the regional projection is always the highest in the east coast of the US. That's correct.
Thanks, that helps a lot, Vivian and Ron.
We have a question from Ron, it looks like. Ron, would you like to unmute?
Yeah, hi. Could you just tell us more about this atmospheric circulation feedback and why it's not captured by the models? Is this just something that's showing up now as like just unforced variability and not a trend, and there's a possibility that it could be part of the trend in the century? I mean, why is this not captured by the models? And what is it? Thank you.
Well, yeah, it goes in the direction, as you say, it's variability which is not captured by the models, which may be related to, well, the model is maybe tuned to the mean state, but that not necessarily means that it also represents the variability of the atmospheric circulation correctly. And this seems to be kind of preferable situations where you get a lot of warm air advection from the south to the Greenland ice sheet, which appeared a lot in a couple of years with the high melt, and they don't show up in the models. And whether that's forced or not, I think the debate on that is open. It's the same with the enhanced basal melt around Antarctica, particularly the Thwaites and Pine Island Glacier regions. There's a lot of warm water in those regions, leading to enhanced basal melt, leading to retreat of those ice shelves. But whether that is forced or variability, in the case of Antarctica, ocean variability, and in the case of Greenland, atmospheric variability. That's not settled because the observational records are too short, I would say, to firmly conclude this. But that means that you have to capture it in your high-end estimate, I think, because you cannot exclude it, that this is true. But it may be that in 50 years from now, the whole basal melt discussion around Antarctica has settled because the water cooled in those regions. If you're very optimistic, you can believe that, but I rather would not rely too much on that.
It's really interesting. Do you happen to know offhand who wrote this recent paper about the Greenland feedback?
Delhase.
Delhase.
There are two papers, one from 2017 and one from 2019. It's a French name, so be careful with the spelling. Mathieu can help you out. I think it's Haisse.
Haisse.
At the
Great,
end.
thank you.
Should be Delas, which is fairly easy to pronounce, I think. I have one quick question, Roderik, if it's not too late.
Sure.
So I see here on your last slide a long list of things to improve that we don't do well. I was wondering if you had a preference in terms of if you had to target one process, one aspect that models should do a better job at, which one would it be?
And from the sea level perspective or the high-end sea level perspective, I would say that we really need to get a better handle on the breakup ice shelf, the timing of the breakup of the ice shelves, because that's the critical point we have to prevent. I mean, as long as these ice shelves are in place, we don't get high-end values. At least we can adapt to it. And as soon as that happens, if the ice shelves break up, there will be physical processes leading to high sea level rise, and whether that's enhanced basal melt or Mickey, from a stakeholder perspective, I would say I don't care. Physically, it's very interesting, but to have a better understanding of Mickey, but the stakeholder is already screwed up by the time that Mickey is going to be critical. So I think as a community, we should try to focus more on the breakup of ice shelves, the timing of it, which is extremely complicated because it's related to atmospheric changes and ocean changes. And it's very often that we treat that in isolation. So, and that's not fair to do because there is no reason to assume that the ice shelf breakup will be completely atmospheric driven or ocean driven. We don't have evidence for that, I would say. So trying to get those processes in Earth system models is very important. And of course, there are a lot of people working on that, but it's also very complicated. So we will not have solved that in a year time. I mean, this will take time.
We have a comment in the chat from Gavin. So he's talking about Antarctica and he's saying the forcing doesn't necessarily just mean CO2 when we're interested in the change of the Antarctic ice sheet or melting. Sure. It's also things such as the ozone hole, right, which is impacting surface winds, etc. And we expect this to reduce over, or as maybe we think might have reached a maximum in 2010 or so. Yeah. I'm not sure what the status of that is. Whether I think we recently discovered there's a new source of CFCs, which is perhaps having a new impact.
Yeah, but sure I think that's
right, it is diminishing.
That's a little bit supporting my vision that it's important to capture these things in Earth system models, because then you can have the feedbacks between these different mechanisms at least somehow incorporated and not in isolation. There's also a lot of discussion recently on the ocean temperature changes around Antarctica. There was this paper from René van Westen from our oceanography department arguing that high resolution ocean models show no change in water temperatures in contrast to the low resolution CMIP models. And well, if that is true, then this has major, this can have major effects for the basal melt changes around Antarctica. So that's also an issue.
Yeah, it's a really tricky problem. I was interested in an earlier figure where you were showing the correlation between, I think it was, say, for example, the different components of melt of the Antarctic ice sheet with other components of contributions to sea level rise. Do you know what I mean?
No, I was trying to read the chat, but
I thought it was,
say
yeah,
stop.
no, back, the correlation squares, I thought were really
Oh, the
neat.
correlation squares. That was.
I had not thought about this before. All right, so yeah, just showing how different components may be correlated or anti-correlated with one another.
Yeah, so this plays up particularly if you go to regional sea level changes. It has quite some consequences in the projections, whether you make an assumption on the different correlations or whether you calculate it from the ocean models, the CMIP models. In AR5, they did a pretty ad hoc assumption on the correlations, which you have to do if it's not a fully coupled system. I mean, if you have a fully coupled system, if sea level would be the outcome of every GCM or ESM, then you implicitly resolve and then you go to a stochastic formulation of sea level, but that's not what we do currently. That complicates how you treat these uncertainties. But yeah.
There's more comments in the chat from Gavin. Might be nice to hear from you if you want to unmute, but he's talking about the high resolution models and how they also don't represent ozone and meltwater. It's true,
No.
yeah. But I think the point with high resolution is that we're not representing, or it kind of highlights that we don't have a perfect representation of the small, from the ocean side, at the small scale. You know, we can't represent the baroclinic Rossby wave, Rossby radius effectively.
This paper is really focusing on the eddy resolving properties of the ocean model. So it's not focusing on other aspects of the climate system. So it's limited, and it's also limited in the sense that the ocean model which they used is not an ocean model which resolves the circulation below the cavities in Antarctica. So it's of limited value, but it's an interesting point. We should probably explore more whether it's playing up in other models as well, for instance.
Maybe it's impossible to do, but I would love to see a presentation where someone goes through this and lists all the small scale or various processes that we think we might be getting right and getting wrong, and putting on order of magnitude what is the greatest impact, say, for example, heat content on the shelf. Because it's true, there are just so many processes, right? So like maybe we poorly resolve processes leading to bottom water formation. We have poor representation of katabatic winds and polynya. There's sort of like a very large distribution of really interesting processes that we're not getting. Sorry, are there any other questions from anyone after my ramble? Silence.
Silence. Yeah.
Ah, Klaus is clapping. We're about we're closing in on noon here. Thanks again, Roderik, for a really interesting talk. Thanks everyone for the discussion, and yeah, thanks again, Rod, and hopefully everyone has a great rest of the day.
Yeah. Have a good lunch to you. I go for preparing my dinner.
Fiona and Matthew are saying thank you.
Yeah, I see. And if anybody has questions, you know to find me somewhere, I guess. And if you have further questions, feel free to come back. Okay.
Yeah, thank you. And this talk will be put online if anyone wants to check over anything. It'll be on the GIS YouTube.
Yep.
Yeah, thanks. Thanks very much for a really interesting talk, Rod.
Yeah.
If you can think of anyone within your group or in the community that you think might be interested or nice to have speak, please let us know. It's always great.
Yeah, I think you already have one on the list. The very last one is from our institute as well. That's Michiel.
Oh yeah.
Yeah. I think
Cool.
in September or so. Yeah.
But if you have any like masters, if you have any students that you think it might be good for them, I don't know.
Yeah, I'll have an idea. I'll try to mail him and see what he thinks. Yeah.
That would be wonderful.
Yeah.
Okay.
Okay. Thanks and good luck. Okay. Bye-bye.
Okay. Bye.